Let's start our seminar, and we start with solution of linear homogeneous system, and the problem to find the basis in the space of solution of this linear system. And let's write find solution. Let's write the matrix of this system, and I write the last equation as the first row of our system. 1, 1, 1 minus 3, 6. I wrote the coefficients of the third equation. The coefficients x1, x2, x3, x4, x5. The second row minus 1, minus 1, 2, minus 3, 5, and last row 2, minus 1, 0, 1. I can use the arbitrary order for the equation. In the linear system, I can change the order of the linear equation. The same way, in the matrix, I also can change the order of rows. And more convenient for us to change the order of the equation. The explanation is the first elements in the third equation I equal 1. It's more convenient for calculations. And we will use the Gaussian elimination method, and our claim to obtain the 0 in the first column. For this claim, I will use the following elementary transformation. First of them, I put the second row is equal second row plus first, and third row is equal third row minus 2. Oh, I'm sorry. R. I rewrite the first row 1, 1, 1, minus 3, 6, 0, 0, 3, minus 6, and 11. Minus 0, minus 0, minus 3, minus 6, and minus 11. And the last step, I add the second row to the end, and I put third row is equal third row plus second row. First row I rewrite, second row I also rewrite. And last row is equal 0. Last row is equal 0. I'm going to get the reduced echelon form on this matrix, and I put the second row is equal the ratio 1, 3 times R2. I consider the column which contains the leading element. I obtain the following leading element, this element and this element. And I put the leading element equal 1, and I transform this matrix in the form when the columns which contain the leading element form the unit matrix. And my next step to obtain on this place the 0, and the elementary transformation is following: R1 is equal R1 minus R2. I subtract the second row from the first. 0. I rewrite the second row, and I subtract 1, 1, 0, minus 3, minus 2, minus 1, 6 minus the ratio 11, 3, and I obtain the ratio 7 times 3. And I obtain the most simple reduced echelon form for our matrix, which equivalent the solution of our linear system. And I can write the solution. I have the following independent variables x1 and x3, because the columns, the first and third columns form the unit matrix, and I have the following solution: x1 is equal minus x2 plus x4 minus 7 divided 3 times x5. X3 is equal to x4 minus the ratio 11, 3 x5. I obtain the general solution of our linear system. After them, I can obtain the basis in the space of solution. The arbitrary solution has the following form. I have x2, x4, and x5, 3 independent variables, and 2, x1 and 3 dependent. I can put the values of the independent variables equals an arbitrary real numbers. And my claim to present this general solution as a linear combination of the basis solutions. From the algorithm which was done on the today's lecture, the numbers of the basis solution equal to the number of the independent variables, and we have three basis elements, and we have x1, x2, x3, x4, x5. x5 the variables, and x2, x4, and x5 be the independent variables, and bar x1 the first basis solution. I suggest to denote the basis solution by the numbers E1, E2, and E3. And I put the first independent variables x2 is equal 0, and other independent variables x4 and x5 I put x2 I put is equal 1, and other independent variables x4 and x5 I put equal 0, and I can calculate x1 is equal -1, and x3 is equal 0, and I obtain the first basis solutions. For the second, I put x2 is equal 0, x4 is equal 1, x5 is equal 0, and I calculate x1 is equal 1, x3 is equal 2, and I obtain the second basis solution. For the third, I put x2 equals 0, x4 equals 0, x5 is equal maybe is equal 1. I put arbitrary numbers. Maybe more convenient put is equal 3. put equal 3. In this case, I obtain the values of the other coordinates as the integer numbers. If I put this variable equal 1, I obtain the rational numbers. Maybe less convenient. And is equal 3, and this variable 0, this 0, and this is equal -7. And this is equal -11. And I obtain three vectors. And I assert that any linear combination of these vectors is equal is solution of this system. Easy to see, more convenient for us. We write these numbers as columns. X1, E1 plus let's consider the arbitrary linear combination lambda 1 E1, lambda 2 E2, lambda 3 E3, and I obtain this arbitrary solution X. And easy to see that in this case E1 is equal -1, 1, 0, 0, 0. Lambda 2 is equal 1, 0, 2, 1, 0. Lambda 3 -7, 0, -11, 0, 3. If I add these columns, I obtain minus lambda 1 plus lambda 2 minus 7. I'm sorry, lambda 3. Lambda 1 lambda 1 to lambda 2 to lambda 2 minus 11 lambda 3. lambda 2 and lambda 3. And the arbitrary solution x1, x2, x3, x4, x5. And I can rewrite this equality as the following system. x1 is equal minus lambda 1 plus lambda 2 minus 7 lambda 3. x2 is equal lambda 1 lambda 1 x3 is equal to lambda 2 minus 11 lambda 3. x4 lambda 2, x5 lambda 3. Easy to see that I obtain the parametric form on this equation. If in this equation I put the independent variable x2 is equal lambda 1, x4 is equal lambda 2, and x5 is equal lambda 3, I rewrite this solution in this parametric form, which equivalent this form. If I substitute in this equation, I change lambda 1 by x2, lambda 2 change by x4, and lambda 3 change on x5, I obtain, I'm sorry, my mistake. Three lambda 3, I'm sorry. 3 lambda 3. And if I put x5 the ratio lambda 3 lambda 3 is equal x5 divided 3. I put this equation. Let's substitute. Let's substitute. Let's substitute. x1 is equal lambda 1 is equal x2 minus x2 lambda 2 is equal x4 and lambda 3 x5 divided 3. And I obtain the first equation. x3 is equal to lambda 2 to x4 minus 11 lambda 3 is equal x5 5 divided 3. And I obtain the general solution of this linear system. And we obtain that the linear combination of this solution is a solution of is general solution of our system, and easy to see that any solution of our linear system can be present as such a linear combination. And easy to see that these vectors linear independent. Let's check this fact and prove that this vector is linear independent. Easy to see that if this linear combination is equal to 0, let's suggest that linear combination is equal to 0. We can consider the second term in these columns, lambda 1, which is equal to 0. The first terms, lambda 2, is also equal to 0, and last term is also equal to 0. And we obtain that all coefficients of this linear combination equal 0. It means that linear combination is linear independent. And the proof of the last theorem is repeat this reasoning. We repeat the proof of the theorem on this partial problem in this partial case. Maybe any question? Do you understand my reasoning? Okay. No students. Okay, let's consider the second problem. I repeat. I suggest consider the other general linear system. Rewrite this linear system in the matrix form. We obtain the following matrix: 2, minus 1, 3. The first expression. We have the 4 variables: x1, x2, x3, and x4, and the coefficients for the fourth variables x4 is equal to 0. We can write, and I must write 0 on the last place. second equation 0, 1, 0, 1. Third rows 3 minus 2, 3, 1. And last rows 0 minus 1, 0 minus 1. Let's simplify. Let's simplify. Let's rewrite the first row as the sum minus R1 plus R3, and we can also to add to the last row the second row. R4 is equal R4 plus R2. The first row, we change the sign, and to add the third row, minus 2 plus 3 is equal 1, plus 1 minus 2 minus 1, minus 3 plus 3 is equal 0, 0 plus 1 is equal 1. The last row 0, 1 minus 1, 0, 0 plus minus plus 1 minus 1, 0. Next step, R3 is equal R3 plus minus 3R1. We write first and second rows. And to add to the third rows the first, which multiply on minus 3. Minus 3 plus 3, 0. Minus 1 minus 3, 3. 3 minus 2, 1. 3 minus 3 plus 1 minus 2. Minus 2. The next step, to add to the third row second, which multiply onto minus 1. We rewrite the first row, second row, and last row is equal 0, 0, 3, minus 3. Multiply the third rows on the ratio 1, 3. Where 3 is equal. We obtain the following matrix. We write first row, second, and and we obtain the following matrix. And we must to get in the first rows on the second place 0. For this we add to first row second row. We rewrite all rows. We change only first rows and rewrite other rows. One, 0, 0, 2. And we obtain that the first 3 columns form the unit matrix. And we obtain simple reduced echelon form, which equivalent the solution, the general solution of this system. And the solution is the following: x1, x2, x3. x1 is equal minus 2 x4, x2 is equal minus x4, x3, x4. We obtain the general solution. The parametric form of the solution is following: x1, x2, x3, x4. x4 is equal u, x3 is equal u, x2 is equal minus u, minus 2u. The parametric form of our solution. You can find the basis. We have only one independent variables, x4, and it means that the basis contains only one vectors. E1. We have the variables x1, x2, x3, x4. We obtain x4 is equal unit, and x1 is equal minus 2, x2 minus 1, x3 1. And we obtain these vectors. Is any solution x, x1, x2, x3, x4 can be expressed in the term of these vectors: minus 2, minus 1, 1, 1. We can multiply this vector by any coefficients u, and we obtain exactly parametric form of the solution. We obtain that is equal minus 2u minus u, u. This equality of these two vectors can be written as a linear system. This linear system is equivalent to this matrix equality. Okay. Let's consider one more example. And consider the solution of inhomogeneous linear system. If we have arbitrary linear system, and corresponding homogeneous linear system. Let x0 be the solutions, be the one solution of homogeneous linear system, and x1 is a solution of the inhomogeneous linear system. This linear system we can rewrite in the maybe more simple form as a sum tuple of the equation the linear system is some array of the equation a(e1), x1 plus and so on, a in xn is equal bi. And consider the sum of the solution of homogeneous system and inhomogeneous linear system. Let's x be the sum x0 plus x1. I assert the sum of the solution is also a solution of non-homogeneous linear system. If we substitute this equation, the sum x1 0 plus x1 1 and so on, and after we can rewrite this expression in this following form. And the sum of the first summands is equal to 0 because these variables is solution of homogeneous linear system, and this sum is equal bi, and we obtain that the sum of solution of homogeneous linear system and non-homogeneous linear system, corresponding non-homogeneous linear system, is solution of non-homogeneous linear system. Contrary, if we have two solutions of non-homogeneous linear system, if its difference be the solutions of homogeneous linear system. So from this fact it follows that any solution of non-homogeneous linear system can be present as some distinguished solution of non-homogeneous linear system plus some solution of homogeneous linear system plus general, and from this fact we obtain that general solution of non-homogeneous system is the sum, the sum fixed solution of non-homogeneous system and general solution of homogeneous system. From geometrical point of view, the solution of the homogeneous linear system is some hyperplane which pass through the origin of coordinate system, and solution of corresponding non-homogeneous system is the other plane which parallel initial, and any point of this plane can be present as a sum this point is vectors which coincide the origin of our coordinate system and the point of this plane, and these vectors can be present some fixed point on the plane plus the arbitrary vectors which parallel this plane. This fixed point is a partial solution, and this arbitrary vector is a general solution of homogeneous linear system, and this presentation corresponds this geometrical picture, and we can use this geometrical interpretation, and we describe the solution of arbitrary linear system as a sum of the partial solution. Partial means some fixed solution of linear system and the general solution of the corresponding homogeneous linear system. Спасибо. Let's continue. And consider the following linear system: x1 plus 2x2 plus 3x3 plus 4, x4 is equal 3. Is equal 7. Okay. And let's solve this arbitrary linear system and present the general solution of this linear system as a sum of some partial solution of this linear system and general solution of corresponding homogeneous linear system. And the last solution we present as a linear combination of the basic solutions. Let's write the matrix, the augmented matrix of this system. And using the Gaussian elimination method, reduce this matrix to the echelon form, and after the reduced echelon form and simple reduced echelon form. We can put two rows is equal R2 plus minus 2 R1, R3 we put equal R3 plus minus 3 R3. The first rows we rewrite. Second rows we add 2 plus minus 2 is equal 0, minus 4 plus 5 equal 1, minus 6 plus 6 0, minus 4 plus minus 8 plus 8 is equal 0, minus 6 plus 7 is equal 1. The same way, minus 3 plus 3 is equal 0, minus 6 plus 10 is equal 4, minus 8, minus 9 plus 9 is equal 0, minus 12 plus 12 is equal 0, minus 9 plus 13 is equal 4. After that we can subtract from the third row's second, multiply minus 4, multiply 4, and we obtain 1, 2, 3, 4, 3. In the last step, we put R1 is equal R1 plus minus 2 R2. You write the second row and the first row is equal 1, 0, 3, 4, 1. We obtain the simple reduced echelon form. And after that we can obtain the general solution of this linear system. We have two dependent variables x1, x2, and other variable are independent. Minus 3 x3 minus 4 x4 x2 is equal 1 and plus 1. And if we can to solve corresponding homogeneous linear system, we must put the free term equal 0 and repeat this transformation, and on the last step we obtain the following general solution of the corresponding linear system. x1 is equal minus 3 x3 minus 4 x4 x2 is equal 0. The last step, let's obtain the general solution of the corresponding homogeneous linear system as a linear combination of the basic solutions, and obtain some partial solution of this homogeneous linear system. For this, the partial solution x1, we can put the independent variable, we must fix independent variable. For example, we can put the values of this variables equal 0, and in this case, if you put x3 and x4 equal 0, we obtain x1 is equal 1, x2 equal 1, and partial solution of the non-homogeneous linear system is equal 1, 1, 0, 0. The general solution of the corresponding homogeneous linear system. We have variables x1, x2, x3, x4, and x3 and x4 independent variables. We have two basic solutions let's denote the solution by E1, E2, and put the value of the first independent variable x3 equal 1, x4 is equal 0, x2 0, x1 equal minus 3. If we put x3 equal 0, x4 equal 1, we put x2 0, x1 minus 4. And we can write the general solution of the corresponding homogeneous linear system as a linear combination of the basic solution u E1 plus v E2. And in this form we obtain the following expression: u times column with components minus 3, 0, 1, 0 plus v times the columns with components minus 4, 0, 0, 1. And the general solution x is equal x1 plus x0, 1, 1, 0, 0 plus u minus 3, 0, 1, 0 plus v minus 4, 0, 0, 1. This expression is equivalent parametric form of this expression. We can rewrite the general solution in the parametric form, namely x1, x2, x3, x4. We put x3 is equal u, x4 is equal v, x2 is equal 1, x1 is equal minus 3 times u minus 4 times v plus 1. This parametric form is equivalent, this expression is to see if you rewrite this expression, we obtain x, the column matrix with coordinates x1, x2, x3, x4. And the right side we have the following sum: 1 minus 3u minus 4v. The second component is equal 1, third component u, and last component v. And easy to see that this equality of the two vectors is equivalent this linear system. This equality is equivalent the equivalence for corresponding components. This equality means that x1 is equal 1 minus 3 u minus 4v, this first equation. The equality for the second component, x2 is equal 1. This second equation, x3 is equal u. The third equation, x4 is equal v, the last equation. So the parametric form for solution of non-homogeneous system is equivalent to the presentation the solution as the sum of the general solution of corresponding homogeneous system as a linear combination of basic solution and some partial solution for the non-homogeneous linear system. But such presentation, easy to see that this presentation is not unique. We can choose the values of parameters u and v by various ways, and we have infinitely many such presentations. We can change the basis, and we can change the fixed point, the fixed partial solution, and we have infinitely many such presentations. But this presentation essentially are essentially equivalent. We can express one of them in terms of other, and contrary other in terms of the first presentation. Okay, we have more time, and we can consider maybe one or two other examples. And we have some parametric, some linear system with parameter. We have the following simple linear system: x is equal a to x plus y plus 3z is equal b, x minus is equal c. We have infinitely many linear systems because the right hand of this equation some parameters a, b, and c, and these parameters can be arbitrary real numbers. And our claim to find the solution of this linear system as a function of this parameter. We must express the solution. The solution is a three-tuple of the real numbers, the values of variable x, y, and z. And we must express the three-tuple in terms of these parameters a, b, c. And we must show maybe for the some values of these parameters, this solution this linear system has no solution. Has no solutions. Okay, let's start and solve this linear system. We can rewrite this linear system in the matrix form, and we obtain the following matrix: 1, 2, 1. The first column 2, 1, minus 4, minus 1, 3, 9, A, B, C. Let's start. let's transform this matrix into echelon form. R2 we put equal R2 plus minus 2R1, R3 is equal R3 plus minus 1R1. We write the first row 1, 2 minus 1A, the second 0 minus 4 plus 1 minus 3, 2, I'm sorry, it's right, minus 3, 2 plus 3 is equal 5 minus 2A plus B. The last 0 minus 6 10 minus A plus C. The last step, let's add to the third row, second row, which times minus 2. First row 1, 2 minus 1, A, 0, let's multiply the second rows to minus 2 and to add to third row 0, 0, 0, 0 for A minus 2B minus A plus C. And we obtain that our linear system has the solution only in the case when C is equal B minus 3A. Only in this case. But the values of the parameters B and A can be chosen as arbitrary real numbers. After them we can obtain the solution of this linear system. If C is equal difference B and 3A, C times A, B minus 3 times A, this linear system has a solution, and we can obtain the solution. We obtain the reduced echelon form. For this, we put R3 is equal the ratio minus 1, 3 times R, or I'm sorry, R2. If C is equal minus 3 plus B, the last rows is equal 0, the second rows 1 minus 5 divided 3 minus the last step, we put R1 is equal R1 plus minus 2 R2. We obtain the following. Zero, 7 divided 3 A plus minus 2 and we obtain the following solution. X1 is equal minus 7 divided 3 x3 plus the ratio 7 3 times A plus the ratio 2 3 times B. X2 is equal the ratio 5 3 minus the ratio 2 3A minus 1 3B, and C is equal B minus 3A. And we have two cases. If C is not equal difference B and 3A, this linear system hasn't a solution. In the case when we have such equality, this linear system has infinitely many solutions, which depends from values from arbitrary values of the second variable x3 and from values of the parameters A and B. And A and B. We have for any fixed values of these parameters, we have infinitely many solutions. Okay. We have сколько? 4. Let's try to solve maybe one more, maybe short task. let's solve some task. The solution to reduce the solution of this task to the solution of some linear system. Find A, B, C such that we have the following equality. We can use general denominator to this rational fraction, and we obtain that the right hand of this equality can be rewritten in the following form. And we can write the equality in the following form: 2ax square plus 2b minus a x minus b plus c x square plus 2c. And we have the equality of the following two polynomials. Easy to see that the equality of these two polynomials can be only in the case when the corresponding coefficients are equal. We can put the values of variable x equals 0, and easy to see that the free term 2c minus b is equal to 3. After them, we can divide this equality onto x and put also x is equal 0, and easy to see that the coefficients for the x, 2b minus a, is equal minus 1. And the same way, we obtain that 2a plus c is equal 1. And we obtain the following linear system when the a, b, and c are the unknowns. Namely, we have the following matrix 2, 0, 1, 1, minus 1, 2, 0, minus 1, 0, minus 1, 2 is equal 3. And to solve this system, we find the values of the parameter a, b, and c, and obtain the equality and rewrite the left side in this more simple form. I have no time. Thank you for your attention.